Okay, off we go. So starting with a new section today. And this is the beginning of actually a really long discussion. Sort of the, in some sense, it's a preview, I'll say, of what's going to be one of the big culminating conversations of the course. Chapters 6 and 7, basically, are going to be, roughly speaking, about the calculus of vector fields. So let's talk about what is a vector field. Well, and tell you what I'll do also. Let me address the sort of question of, okay, well, if we're not going to get to the calculus of vector fields until chapters 6 and 7, why are we introducing it now? And I'll give you two answers to that question. One is because the book does. The other, why does the book do it? It's so that you can have a little time to kind of digest the concept, right? So that we're not introducing a brand new concept and then furthermore talking about challenging ideas concerning the calculus of that concept all at once. So it's a pedagogical move. Okay, so here's the big idea. Roughly speaking, a vector field is something like that. That's what we call a two-dimensional vector field. This is what we call a three-dimensional vector field. So I just want to start with the visual impact. It's, kind of like that. Okay, now let me be more precise. What do I mean by this? What do I mean? I mean that at every point, such as that point right there is an associated vector. And we typically draw the vector with an arrow whose tail is at the point in question. So you give me any point that I have in green there, like that green R. There's an associated vector drawn like so. And you can see this is the case for all, every point I have. Obviously, I can't do this at literally every point in all of the XY plane, but I've drawn what you might call a representative sample. And at each one, there's an associated vector. And, you kind of, I'm going to say, interpolate in between. Your imagination can kind of fill in the blanks. Okay, how are we doing? Is everybody on board with that as that's what the picture is? Okay. And now, make the observation that ultimately what that is then is a function. It's a function from Rn to Rn. In this case, from R2 to R2. And it might not look like it. That's certainly not a graph of such a function. It's not a graph. It's not a level set. It's not a parameterization. This is, I've kind of lost count now. This is picture construction number 5 or something, right? So we've put together lots of different kinds of pictures. And this is not like any of the ones we've seen before. In particular, though, here's how it works. These points, right? The input to the function is the vector in Rn. That's the position vector for whichever point you're talking about. And then the output is what we call the field vector, the arrow that we draw, the vector that we draw with said arrow at that point. Okay, so it's kind of a weird way to think about it. A lot of people, most of the time when you think about a vector field, you don't think, it's a function. You think of it as, it's one of these kinds of pictures. But then when it comes time to actually write this down algebraically, and rubber meets the road, we got to get stuff on paper, it's important to be able to recognize that it is a function. Okay. Likewise, in 3 dimensions, for every point, there is an associated vector. And again, the points are the inputs, and the field vectors are the outputs. Like so. Okay, so let's see some actual examples, a couple of quickies. So this first one that I have, the inputs, namely these points at which I've drawn a representative sample of the vector field. At each one of those, the field vector is 2, 1. That's our formula for the field vector at any point x, y. 2, 1 is the formula. And if you think about it, that's not much of a formula. In fact, it's a constant. So I'm going to represent it I like to represent constants with gray. Sort of an aesthetic choice. But notice that's in fact what we have here. These are all the same vector, 2, 1. Now, reminder, We do have to think carefully when we say these are all the same vector. We draw vectors with arrows for lack of better alternatives. Don't lose sight of the fact that arrows and vectors aren't really quite the same thing. An arrow is something you draw with a pencil or a pen, right? It's a thing, it's a picture on the page. A vector is just a direction and a magnitude. And we use arrows to represent vectors, but you have to draw the arrows somewhere. Arrows themselves have a location because that's how ink works, right? But the vectors they represent don't. So a little bit weird to say, but this is all the same vector. All right. Okay, here's another one. This is another sort of special one that gets used, comes up quite a bit. For every input point, here's the formula for the field vector. At the point x comma y, the field vector at that point is x comma y. Now that obviously you notice, oh my gosh, the input's the same as the output. A couple of thoughts might be rolling through your head. You might be thinking, oh well, this must be like it's kind of like f of x equals x, right? In single variable calculus, it must be like a straight line or something. It's not, because it's not a graph. And again, very importantly, when you think of y equals x and think of that as being a straight line, well, no, its graph is a straight line. Right? This is not a graph. This is a totally different picture. So how do we figure what this represents? Well, the input point has the same formula as the field vector. Okay, so let me say that differently. The input point, don't forget we could represent points with position vectors. So the input position vector is the same vector as the field vector. So, okay, great, cool. This is my position vector. That's my field vector. It's just I can't leave it like that because that's not how we draw vector fields, right? The vector field construction, draw a picture of a vector field. The tail goes at the point. And so I'm just going to draw that position vector following our artistic rule. And now I don't really need that position vector anymore. It served its purpose. And here you go. This is, for this point, that's the field vector. And you see this vector field, wherever you are, points radially outward from the origin. And the further you are from the origin, the longer your field vector is. So that you put it all together, do this for every point in the plane, and you get that. Okay, so this is a good example to kind of chew on, and to, again, we're building experience in your minds of how to look at formulas for vector fields and see what they look like. Again, with this brand new construction of how to draw things, completely different construction. So that's what this one is. Okay, here's another one. Well, we're going to play a similar game at any given point. Let's say that one. Here's a formula for our field vector, and now you will notice, let's look at the algebra, forget about the geometry for a second. You look at the algebra of the x and y that go in. Okay, it's not exactly the same, but I see the same x in there, and I see the same y in there, and you might even notice this dot product is 0. Kind of a good little thing to keep your eye out for. You'll also notice that this green position vector and the blue field vector have the same magnitude. But immediately tells you that this is, in fact, a vector that's orthogonal with the same length as the field vector, as the input vector, And so right off the bat, we know it's either this one or this one, and then the question is, which of those two is it? That's all that that's all that we can't deduce just at a glance. And, plug in some points and you can persuade yourself pretty quickly it's this one. Now, I am going to leave an exercise for y'all to do. I think this is very doable. Remember, linear algebra, prerequisite for this course, and in particular, I don't want to overstate it, but one of the big things that I need y'all to be good at in this course is the idea that when you have a linear transformation, that linear transformation can be represented by a matrix. Matrices are understood by their columns, and those columns, there's a simple formula, the columns are the images of the standard basis vectors. So that's a very important prerequisite for the course. And if you apply that to the idea of a quarter turn counterclockwise rotation, what you'll find is that's what's happening here. Namely, the relationship between this input position vector and this output field vector. And yeah, I know I didn't draw it where I'm supposed to, right? But again, this is, it's a vector. You can draw it wherever you want. It's just not part of the graph picture anymore. But this relationship, what the vector field does to the input position vector to get the output field vector, quarter turn counterclockwise. So this is a great exercise. I encourage you to think that through, fill in the appropriate blanks, and with that understood, then that's another way to justify that this is an arrow pointing like so. And thus, that this vector field is what I like to call the stirred pot. So imagine that you're looking from above down on a pot. Maybe you're cooking some pasta, right? And somebody has stirred the pot. And, well, this describes the flow of the water in that stirred pot. Okay. All right. How we doing? Everybody happy? Yeah.
So, what we're drawing is another picture for a function.
Yep.
Of that goes from any
from any Euclidean space to itself, right? So it does have to be Rn to Rn. It's got to be the same. Absolutely.
This is just another picture. Like, it's not a graph. It's not.
Correct.
Okay.
Correct. Yeah, you're right. It narrowly applies only to this category of functions, Rn to Rn. Right. Yeah. Okay. Here's another one. This one's surprisingly important given how weird the formula is. You see the cube in the denominator. How could a cube be important? How often does that come up? It actually comes up a lot, believe it or not. And here's the justification. If we look at this formula, and if I kind of move things around a little bit, now that's just a little bit of algebra, no tricky curves there, but I just moving things around a little bit. Check it out. At any point, wherever you might happen to be, for any point, this is the unit vector pointing in the direction of that position vector, right? So for that position vector, what I have in blue is the unit vector pointing in that same direction. So, and notice that unit vector pointing in that same direction is always radial. It's always directly outward away from the origin along what you might call sort of parallel to that sort of kind of radius, if you will. So that's the term radial. And now what else can I say about this? Well, aside from being radial, notice that this is inverse square. Right? Inverse square literally, right? So it's a square in the denominator. And in particular, it's inverse square of the distance from the origin. So radial inverse square. And now just a real quick flashbacks. If you've taken a high school physics course, and if that course included a discussion of how gravity works, right? You might remember, oh my gosh, that's exactly how gravity works. Gravity is always along that radial line. It's in the direction of between the two masses, and it's inverse square with the distance. So, in fact, that's one of the big reasons why this vector field matters. This vector field matters because it describes gravitational fields. Kind of a big deal, right? It's a thing, right? And side note, it's also the formula for electric fields. different constants, different units, yeah. But structurally, mathematically, it's pretty much the same formula. Yep.
Shouldn't there be a negative?
There's a constant, and in this case, that constant's negative, and so that's why it's inward. Yeah, good catch. But yeah. So I wanted the picture to represent gravitational field because that's kind of the most relatable one, and yeah, gravity has a negative value for that constant. Yep. Right. Okay. So heads up, good thing to be aware of. And be on the lookout for this construction right here, because when you see that, that means you're talking about something that's pretty physically natural, and that might be a useful observation. Okay, real quick observation here. I forgot to hit the button like so. Gradients always point uphill, and yeah, well, of course. We already knew that. We talked about this back in section 2.6. Gradients point in the direction of fastest increase, or sometimes known as the direction of steepest ascent, sometimes known as uphill, right? So, sure. Why are we mentioning that old piece of information in a discussion of vector fields? The reason why is because the gradient is a vector field. We didn't think of it that way at the time, right? Our attention at the time was, let's look at a single point in the domain, and let's think about the gradient at that single point. We were only looking at that one point, and so the gradient was a vector because we were only looking at one point. But notice, and this is a nice little easy example, if you look at this function, right, and you take the gradient, and here's the formula for the gradient, you see it's a formula. That means that at different points, different x and y, there are different gradient vectors. So, weird thing to think about, but the gradient is, in fact, a vector field. And it's a vector field that always points uphill. Is that cool? I should say always points uphill on the graph. Let me go ahead. Again, you got to keep track of your pictures and make sure you're interpreting the right kind of calculus in the right kind of pictures. Okay. Okie dokie. Now let's talk terminology. This is a slightly awkward point, and I tend to get more upset about these kinds of things than other people. I should probably chill out a little bit, but I think this is worth observing, and for whatever it's worth, this used to confuse me. Right? And so part of why I'm uptight about some of these things is I don't want them to confuse you like it confused me. Right? So, first I'm going to start with what I think the terminology should be. Right? And as with many other examples, I'm kind of hoping this will catch on. Right? Anyway, so here's the big idea. If you have some function and if you compute its gradient, no surprise, that gradient we refer to as the gradient because it's the gradient, right? I mean, that's obvious. Of course, I'm being silly. Okay, but here's the thing. If you have a vector field and you say, well, yeah, but what is that the gradient of? Or said differently, if I want to undo the gradient, what should I call this thing? And I propose that antigradient makes sense there. Flashbacks to single variable calculus. You have the derivative, and when you go back the other way to find the thing whose derivative was the thing, well, that's called the antiderivative. Right, so this is just piggybacking off of that previous grammatical construction. I think it's extremely natural. If you say antigradient to anyone, even if they haven't heard the term antigradient, they'll put two and two together and figure out what you mean. Right? All right. Now that said, the more common term is that this is referred to as a potential function. Now, kind of comes out of nowhere. Why do they call it a potential function? And the short answer is because if you're doing physics, which you're not always, but if you were doing physics, and if the vector field represents forces, then the antigradient does relate to potential energy, in the sense that the negative of the potential energy indeed does give you the force. And here's my confusion. What used to really always turn me around backwards, and I blame the terminology, the minus sign. I mean, think about any easy example. I mean, gravity's a nice one, right? Gravitational force is downward. In which way does potential energy increase? Upward. Minus sign. Right? So I think this is awkward. To call me crazy, but I think it's awkward to refer to the negative of something with the name of that something, right? I just find that really uncomfortable. Now, don't get me wrong. I got it. I understand it. I can handle it. I'm not confused about this anymore. I'm painfully aware of this minus sign, right? But it nevertheless, I mean, it remains that it's just a little bit unnatural, okay? And for students that are first-timers, it is a little bit confusing, and I don't really, frankly, see the need to go with the option that presents this confusion. So that's why I pretty much always use the term antigradient in preference to the term potential function. Right, so in this course, I'm going to say antigradient. And just heads up, when you get out of this course and you're taking engineering classes and physics classes, etc., yeah, they're probably going to call it the potential function. And then you're going to have to be like, okay, so I got to deal with that minus sign, and just don't forget about that minus sign. You know, play the game, do it their way, of course, absolutely. For whatever it's worth, I have found it helpful to remember that minus sign by just remembering that potential energy is the negative of the antigradient. It's easy to remember a minus sign when it's a relationship between two things that you have distinct in your mind. And I think distinct words help to keep concepts distinct also. So that's my take. Okay. Sometimes vector fields don't represent forces. Now, reminder, a vector field, in fact, is just a function that you interpret a certain way and draw a certain way. It's a mathematical construction. And yes, it is convenient to represent forces like gravity and electricity. Yeah, sure, absolutely. It's a useful tool for that application. It is also a useful tool for other applications, and I'll remind you, we already kind of saw one. Right? I refer to this as the stirred pot. Right? There's no forces involved. There's a fluid that's, swirling. No forces. Okay. All right, so with that in mind, there's a lot of fluids that we want to be able to keep track of and describe, and therefore hopefully be able to do some math with. Maybe solve some problems in relation to, right? And so here's a bunch of different three-dimensional fluids. They're all different fluids, right? Things you might want to keep track of, and vector fields are a great way to do that. And I like to point out as well, even though we live in a three-dimensional world, there are some two-dimensional fluids, air quotes, that we need to keep track of as well sometimes. And, surface water is the sort of the easy one to make reference to. So if you think about how, water flows on the surface of the earth, rivers and stuff like this. Have y'all ever heard of this thing called the Continental Divide? Curiosity. Anyway, there's a thing. I'm sorry?
From the Ice Age movie.
Oh, no, good guess. No, the Continental Divide is a different thing. It exists today. The Continental Divide is a line that goes sort of through the middle of the Rocky Mountains, roughly speaking, and it's defined by, it's the dividing line between points where if you were to drop a water droplet and watch how it flows, some of those water droplets will go into the Atlantic Ocean, and some of them will go into the Pacific Ocean. And the continental divide is the dividing line between those two regions. So anyway, that's in making a reference to how water flows on a surface. That's a two-dimensional fluid flow. Animal migrations is another fun one to think about, and obviously we don't tend to think of animals as being fluids. Any individual, I'm not referring to the fact that the human body is like 93% water. That's not what I'm talking about, right? But if you have like swarms of locusts, let's say, right? Well, okay, it's not a liquid, right? But it is a fluid because it's a bunch of little small things that all kind of flow in some sense together, right? And you think about it, that's what water is. Liquids tend to be made up of little molecules that all kind of flow together. So not that different. And if you're interested in migratory patterns of birds or wildebeests or what have you, thinking of them as a fluid can be a convenient tool. And it's a two-dimensional fluid. Effectively, yeah.
What is the operator for the potential function? Or is it just
what is the like? How do you do this? Like, how do you find the potential function? Is that what you're asking?
Like what? Like for gradient, you have like the del sign.
Yeah.
So what is that?
I hear you. It's a great question. I'm not aware that we have a notation for that. I would just say gradient of little f equals capital F. Yeah, no, there's a case to be made that maybe we should have a notation for that, but I'm not aware of it. Yep.
From this, it seems like if f is differentiable, continuous differentiable, it will always have a vector field, right?
Mm-hmm. Yeah.
But does every vector field have a corresponding function?
That's a fabulous question. And the answer is it unfortunate? Or anyway, the answer is no. And it's actually kind of beautiful in certain ways that the answer is no. There's some cool math that comes out of the fact that the answer is no. But yeah, so it's a great question. In single variable calculus, every continuous function has an antiderivative. No exceptions. They all have antiderivative. You might not be able to write down a convenient formula for it. You might not be able to work out the algebra for it. But it exists independent of our own incompetence. Not so with vector fields. Yeah, there are some vector fields that simply are not the gradient of anything. Yeah, and again, really cool math related to that. And that's one of the big topics in chapters 6 and 7. Yeah. So I'm not gonna. I don't want to go down that bunny hole for the moment, but we will absolutely get to that. Yeah, it's a great question. Okay, so let's talk about what you can do with a vector field representing a fluid, and this is my favorite first example. It motivates a really important construction we'll get to in a minute. So, suppose we have a vector field representing the velocity of representing a fluid, and to be explicit, how we let a vector field represent a fluid is the field vector is the velocity of the fluid. Whatever point R you're looking at, see what the velocity of the fluid is at that point. That's the field vector. Side note, this is one of two very common important ways to represent a fluid flow. There is another one that is also very important. We'll get to that later. For the moment, field vector is velocity. Okay. All right. So with that stated, let me observe that, let's see here if I can, how am I going to do? I'll use green for this. If I have some area like that, and if I have some fluid described by a vector field in terms of its velocity, let's say like that, Reasonable question to ask. I mean, I've got this. I know what the velocity of the fluid is. How much volume per unit time of fluid is passing through that area? Okay, reasonable question to ask. So here's an example. Maybe you're thinking about the water in a river, right? And you've got some net that you put in front of the river, and maybe you're filtering out garbage, right? Or maybe you're catching fish, what have you. Right? Well, you can sit there and measure what the velocity of the water is, but realistically, what are you actually interested in? You're probably interested in the grand total amount of water going through your net. Volume per unit time, because you want to be able to talk about how much are we filtering, or how much volume of water are we going to catch the fish from? Pretty interesting thing to understand. Does everybody see what we're talking about? Okay. So, so we're going to be trying to compute this thing called, let's see, color choice. Did I decide? I don't think I decided. I'm going to use purple. The flow rate, volume per unit time. So how you compute volume per unit time is a pretty straightforward process. So there's some details involved, and don't allow yourself to get intimidated by details. Very often there's a big picture strategy, and then you handle the details as they come up, right? But don't lose your mind over the details. But you just follow that big picture strategy, handle the details as they come, and out will come the answer. And I think that's what's happening here. The big picture strategy is we're just going to consider literally the amount of volume. Let's see, I will use yellow for this. The amount of volume that passes through in some given amount of time, delta t. And if you know how much volume passes through in time delta t, and if you then divide by delta t, what's left is volume per unit time. Right? So that's the big picture strategy. No big deal. And all we got to do then is figure out what is that volume. And a couple of details. Now, let me clean up my picture here a little bit. A couple of details if you want to... wrong color. If you want to compute this volume, well, I think it's an easy pitch that it's the area of the base times what I'm going to call the height. And keep in mind, a height is always perpendicular to the area. That's an old high school geometry formula. Right? Volume is height times the area of the base. And let's see here. What is that height? Okay, the height. Oh, well, wait a second. I've got this vector called n perpendicular to my area, unit vector that is. And what's the purpose of this height? Where did this height come from? Well, the idea of the height is I'm looking at all the water that has flowed through in a given amount of time. And so literally, there is this vector there, right, that I'm going to call the d vector, which I reproduce over here just to get it out of the way. But pretty easy pitch that height is just the n component of the d vector. All right, well, it's kind of all over with shouting at this point. How do you compute a component? Well, components are dot products with unit vectors. Lucky break, n is a unit vector, so literally component is dot product. Excuse me. And then, wait a minute, what is that d vector anyway? Well, the d vector, if you think about it, is a displacement. And displacement, here we go. Displacement is velocity times time. And the vector field represents our velocity. And so we win. Right? We're done here. And the volume per unit time namely, well, let me get into the highlighter mode, namely the flow rate. That flow rate is what's left over when you divide over that delta T, namely it's F dot N times the area. And this is a very important formula, something we're going to use a lot. It deserves a name, it deserves a notation. We call this flux, and we use the capital Greek letter phi. Make sure to use capital, otherwise it looks like a spherical coordinate. Okay. So, yeah, there you go. So this is called flux. Again, natural interpretation. If the question comes up at any point, hey, what's the deal with flux? Why do we care about flux? The flow rate. To whatever extent your vector field represents a fluid flow, flux is telling you how much of that fluid, in terms of volume, let's say, volume, quantity of the fluid per unit time through whatever surface you're interested in. And again, very natural. Okay, yeah.
Where do you get the delta T from?
Oh, because that's what the D vector is. D is this displacement vector right here, right? And displacement is velocity times time. Yeah. Okay, all right. Now, very importantly, this formula, so flux, that symbol, this formula, when your vector field represents the velocity, it represents the flow rate. There is this other way that we sometimes represent fluid flows. We don't always use the velocity. Sometimes we use something different, not the velocity. And the reason why is the answer to the next example that I'm going to let y'all work out on your own. I think this is a very good exercise. It's totally doable. It's mostly a shameless ripoff of what we just talked through, right? And that is, think through, instead of velocity, what if you represent the fluid flow with density times velocity? Let's just say density times velocity. And let's suppose that instead of looking for volume per unit time, let's suppose that you're interested in quantity per unit time. I wrote here mass per unit time, but I wrote mass because we usually think of density as being mass per unit volume. But sometimes maybe you're not looking at a fluid. Maybe again you're looking at birds, and you typically aren't interested in the mass of birds. Typically, you're interested in the number of birds, right? So density appropriate to whatever the quantity in question is, and then quantity, it might be mass, it might be number, who knows? Again, appropriate to whatever kind of fluid you're interested in. So different interpretation of a vector field, different question, and the answer turns out to be the same. Again, flux. Again, F dot N times A. Right, so this is a slightly different interpretation of flux. And you see that flux is interesting in these two different contexts, where if you make different interpretations of the fluid, then flux will have different interpretations in terms of what is it talking about? In what sense do you mean how much fluid per unit time? In this context, it means volume, how much. In this context, it means mass or quantity or, whatever, per unit time. Okay, all right, so this is a great exercise. I want to encourage you to do this on your own. The way you're going to do it is pretty much a copycat, right? So the way we got our hands on this was, we just literally wrote down the volume. And so likewise, the way you're going to get your hands on this is by literally writing down the mass. And by the way, how do you write down mass? Well, it's volume times density. So you're pretty much going to start the same exact way, just with times density. And then it mostly follows through the same. So good exercise. If you get stuck, ask me in office hours. Happy to help. But I think it's educationally useful for you to give it a try on your own. Okay. All right. I hate to say it, but this is one of my favorite pages in the notes, and we just don't have, it doesn't quite meet the bar. So this is optional. You don't have to look at this. You're not responsible for it. But it is a pretty cool conversation. It addresses a different kind of a fluid where maybe the fluid particles don't always flow together, and there's an easy example of this, and that is light. And if you have a light bulb, photons are the fluid particle, and they tend to flow mostly somewhat together-ish. But they don't always. For example, if you have two light bulbs, then the photons, even at the same point, are water doesn't do that. Right? So this is a very different kind of fluid. And how would we describe this with a vector field? And it turns out there's a really nice answer to that question. And again, we don't have time for it, and it's unfortunate. But anyway, if you want to take a look at this, you're very welcome to. I encourage it, but again, you don't have to. Okay. All right. Okay, related idea, something called a flow line. And so do keep in mind that, we're going to, again, think of a vector field representing a fluid flow by way of the velocity. And if you have a fluid flow, and let me go back to a convenient picture. There we go. If you have a fluid flow, like this one, what do you suppose would happen if I dropped a particle, some sort of floating particle, right? Just drop it right onto the top of we got this pot of stirred water, right? How if I put a bay leaf in that pot, what's the bay leaf going to do? Well, it's going to do exactly what the water tells it to do. And in fact, it's probably going to go around pretty much in a circle, isn't it? And again, why? Well, because the bay leaf doesn't have a mind of its own, or free will, or an outboard motor. It's subject to the water. It does exactly what the water does because it can't do anything else. And wherever you might happen to be, wherever the bay leaf is at any given moment, whatever direction the water is going, well, that's the direction the bay leaf is going. Is that cool? All right. So this is the fundamental idea behind the concept of a flow line. So that's, I claim, all that this is saying right here is that bay leaves go where the water tells them to go. And let's just walk through the notation here directly. I've got this particle, right? And when you take a derivative tells you the velocity of the particle. And again, what does the bay leaf do? What's the velocity of the bay leaf? Well, the velocity of the bay leaf is the velocity of the water. Whatever the velocity of the water is, that's what the velocity of the bay leaf kind of has to be, right? As we just discussed a second ago. And now, point of recognition, the velocity of the fluid is different at different points. Where should I measure the velocity of the water to infer the velocity of the particle? Well, wherever the particle is, right? Again, if I'm a bay leaf floating in the water, what the water is doing over there in the point is, no pun intended, that where I am, that velocity of that water, that's the water that's pushing me. Right? So specifically, here it is. Wherever the particle is, the velocity of the fluid, where the particle is, that's what the velocity of the particle has to be. Everybody buy it? Again, this is just a math representation of this, bay leaves don't have the ability to do anything other than what the water tells them to do, right? It's ultimately a pretty straightforward observation. Is everybody happy with that? Okay. Now, quick reminder, don't forget, let me go back to Yeah, don't forget, I mixed my colors, unfortunately, but the velocity of the fluid is the vector field. So that gives us what we call a system of differential equations. Specifically, look at this right here. Keep in mind position has several coordinates, and the vector field, of course, has several coordinates. So when I say that this vector equals that vector, we're actually saying one coordinate at a time, all of the coordinates of r prime must equal to one coordinate at a time, all of the coordinates of f of r. And so this is actually several differential equations that are all kind of linked together in this sense. And so here's a nice little example. Oh, and then whatever the solution is, position as a function of time, that's the flow line, the path that the bay leaf follows. Okay, so an easy example I'm going to let y'all fill in the blanks on is right here. If you look at this path, I got my colors mixed again, sorry. This path, I claim, is a flow line. In other words, if you put that there and there, it's a flow line for this vector field there. In other words, this equation works. So this is a good plug and chug. All you got to do is plug that in. It's good exercise to make sure you see what goes where and what these things look like. The resulting algebra is actually very straightforward. Nothing to it. The harder question that we're not going to address in this course is suppose I wasn't given the flow line at all. Suppose I just had, I've got the vector field. How would I figure out what the flow line is? How would I solve that system of differential equations? That's a harder problem that y'all will solve in Math 353 for those of you who go on to Math 353. All right. So not our problem in this course. Okay, so just a real quick heads up. So we've talked about interpreting vector fields as, I'm going to say a metaphor of forces. Right? And we've talked about interpreting vector fields in the metaphor of fluid flows. And they're physically totally different. They're different physical objects, different physical scenarios that we're describing with the same mathematical construction. So what I've observed over the decades that I've been teaching multivariable is that many students have a tendency to pick a favorite and run with that one. And you can't do that. There are some very important physics applications that we're going to need to be able to do in chapters 6 and 7 that pretty much only make sense in the context of doing the vector field as representing forces. That has to be something that you're comfortable with, because that's going to be the only thing that will really make real sense. And there are other very important physics applications and interpretations that we're going to need to be able to make that really pretty much only make sense if you're thinking of the vector field in terms of fluids. Then you need both of these applications in your mind. You need to be able to think of vector fields in both senses for this course. So don't make a choice, tempting though it may be, right? I don't like that fluid business. I want to think in terms of forces. Yeah, that losing strategy. It's not going to work. Okay, moving along. This is another premature section, arguably. This is another foreshadowing, right, that's going to be big in chapters 6 and 7. And again, why are we doing this now? Well, because the book is. Okay, why is the book doing this now? to plant some thoughts in your mind so that when we get to it, you'll already kind of have certain pictures already sort of, percolated. It'll just help make things make more sense later in the course. So that said, what we're about to do is mathematically very premature. It's going to come out of nowhere, and there's certainly a strong side of me that's not happy about covering this material now, because I'm going to have to say in a couple of big places, trust me, right? And I don't want you to have to trust me, right? I'm not trying to make you think certain things. I'm trying to persuade you of certain ways of thinking, right? So anyway, this is premature in that sense, and I'm sorry about that. Okay, all right, so y'all remember the gradient? Yawn? Check it out. I could rewrite this formula like that. Now, this does take a little bit of, work with me a little bit in terms of the interpretation. What does it mean to multiply? First of all, what is this critter right here? We've got a vector whose elements aren't even numbers. They're not numbers. They're not formulas. Can you do that? Is that a thing? And okay, so reasonable questions there, and the answer is it's a notational shorthand, and it turns out it's absolutely fine. So very convenient notational choice to kind of pull the operators, these differential operators, out, and to think of the f as sort of what these operators apply to. And so the big idea is it's almost like this is a vector and this is a scalar. And what do you do when you have a vector and a scalar? Well, the scalar goes into all the coordinates, kind of like so. So, a little bit of an abuse, but very common, very handy. And notice that when you do that, if you look just at the operator part, just that, just the d by dx, d by dy, d by dz, this thing that I have in purple is not a gradient. Gradient is what you get when you do that to a function. In this way specifically. That's the gradient. The gradient's in blue. This thing in purple, not the gradient. And another common mistake that I see students make a lot is to just call it the gradient. But it's really importantly not. So you got to resist that temptation. So the name that we commonly use for this, we call it the del operator. And it's very convenient notational choice. So, yeah, I'll show you an example of how useful it is. Now, here's my first sort of apology. I'm going to make a definition, and then I'm going to assert why we care about it, and I'm not going to be able to give you any justification at all, because we're not prepared to justify it yet. I will later. The justification for this will be coming. But we don't have the tools just yet. Okay, so here it is. We're going to talk about this thing called divergence, which we denote with div sometimes. And the divergence of a vector field is computed by that formula. I'll give you an interpretation of it in a minute, but anyway, this thing called divergence is computed by that formula. Do notice that it is computed by looking at the individual components of the vector field. Right? This applies to a vector field. And yeah, you're taking x partial, y partial, z partial, but we're not taking x, y, and z partials of the same thing over and over again. We're taking the x partial of just the first component of the vector field, the y partial of not the first component, just the second component of the vector field, etc. So a weird construction, but it turns out to be very, very, very useful. And here's where the notation comes in handy. If you is a little bit of if you think of it the right way. And let me try to get all this on the screen at the same time. Thinking of del like that, and remembering that f is that. And if I were to ask, okay, what might it mean to talk about the dot product? Del dot F. How would you dot this with this? And again, the reasonable interpretation would be to take, well, okay, X, we'll look at the first coordinate here and the first coordinate there. So X partial of F1, and then you'd have Y partial F2, then you'd have Z partial F3. Oh my God, look at that. You get exactly this formula that we just wrote down. So this is a very common terminology, very common notation. Instead of writing div, people write del dot. And in fact, my memories, increasingly fuzzy memories of past life as an undergraduate second major in physics, I saw a del dot more often than I saw a div. This is a really common notation, and not only common, also very convenient. There's some nice advantages, computational advantages to writing it that way. Yes?
So it's not like previously the F can be seen as a scalar?
This little f. Yeah, we're kind of playing like it is for the purposes of interpreting this notational sloppiness.
Okay, but
Yeah.
here you're just taking a dot product of two vectors.
Yeah, but again with the air quotes, because is this really a vector? I mean, it's not three numbers. What vector space does this live in? Which direction does this point? Right? There's some nasty questions that you would have to sort of, if you really wanted to claim it's an actual vector, awkward, right? So the same situation. I mean, I say dot product. Dot product, as we've defined it previously, technically only applies to actual vectors. And this isn't. So this is another sort of, play along and trust that it all works out kind of situation. Does that make sense?
So kind of
Yep.
like we took like a pseudo determinant for
Same deal.
use it for like sound product.
Yeah. So yet another example of a convenient sloppiness. Yeah, just like the determinant fact, just like the cross product formula. Yeah, totally. Yeah. All right. So heads up for that notation. That's going to be very common. So now here is where I really have to apologize when it comes to, okay, fine. Why would I ever care about such a thing? What does this mean physically? What does this mean geometrically? Are we just writing down random stuff because it looks cool? Is this actually good for something? Is this natural in some way? And it turns out that it is. So, again, I don't have the tools yet to be able to justify this. So you just got to bear with me. And I will give you, I think, a persuasive argument to support this claim. When we get to chapter 6 and 7, I'm just going to claim here that it represents, in some sense, the amount the fluid is flowing sort of away from where you're looking. Trust me. Right, again, I hate having to say that, but let me give you an example. Now, this doesn't prove anything, but this is, at least consistent with my claim. Let's look at this vector field. Make sure you can persuade yourself that it looks like this. Oh, yeah, go ahead.
So you worded it as the amount of fluid flowing away from the vicinity of X.
Yep.
So like...
That's right.
But, we could represent X as a point. So why are you saying vicinity? Is that like... Is that something specific, or is it like...
I don't want to get into the detail. I'm having to be sloppy because I don't have the tools to be precise, right? I'll be more precise than you want me to be in chapter 6 and 7, right? For the moment, I don't want to go down that bunny hole either because ultimately to resolve your curiosity will require tools I don't have yet. So let me just speak loosely, and I think my examples are going to justify this loose picture, and we'll solidify all this stuff later. Is that okay? Yeah. Okay. All right. So we've got this vector field. Think through what it looks like. Now, this is very similar to something we saw previously, but this is three-dimensional. So think it through. Make sure you're comfortable if that's what this looks like. And let's compute the divergence, and specifically, I want to compute the divergence at the origin, so my picture will be friendly to my purposes. So we're going to be looking at the origin specifically. Yes, the calculation will go very similarly elsewhere. I don't want to talk about elsewhere. I want to talk about the origin. So we compute the divergence. You play the game. You take these coordinates. Right, you take the Take the appropriate partials. Right, that's the whole del dot formula. You end up with 3, which, for the purposes of our example, the point is that it's positive. And I'm going to say that this tracks with our interpretation. This assertion that I've made, that it represents the sort of amount that the fluid is flowing outward away from the point. And yeah, I got positive. The divergence is positive. The interpretation, therefore, that I'm trying to, at least show an example of, is that the fluid's flowing away from where you're looking. And check it out. Sure enough, it is. Again, this is a tailored, cherry-picked example, right? But loosely speaking, this is kind of what you should think of when you see a positive divergence. And by the way, another nice example to play with, I encourage you to work out the details for yourself. What if I put a minus sign on this vector field? Well, then all the vectors would turn inward, like a gravitational field, sort of, all inward. And also, with a minus sign, this calculation, you would get -3. Negative meaning then, to what extent do you have an outward flow? Well, negative. You would have the opposite of an outward flow, an inward flow, again, consistent with the claim. Is that cool? All right, justification to come later. Now, real quick, let's talk about physical interpretations. This is another thing that confused me for a long time, and we are going to dig into details related to this later. So this is another sort of, let me be sloppy and we'll fill in the blanks later. I just kind of want to plant thoughts and let those thoughts kind of, take a little bit of root. What is this representing physically? And one possibility is that I've got a bunch of stuff here, and this represents whatever that stuff is flowing outward, and therefore how much stuff is in the process of decreasing. And if you got stuff and it's running away from you, you're losing your stuff. You're in the process of the amount of stuff you have is going down. Right? I hope that makes sense. Yeah? Okay. All right. Here's another interpretation. Inconsistent, but perfectly valid, equally valid. It could be that it's not that I have a finite amount of stuff there and I'm losing it. It could be that this is a stuff factory. And it's sitting there churning out stuff. And yeah, the stuff is flowing out, but I'm not losing stuff. I'm making stuff and sending it on. Light bulb, for example. Light bulbs don't have a finite amount of photons that they emit until they run out of photons. Right? It's not how light bulbs are literally generating photons. So, totally different physical interpretations. So how should you think about divergence, and how should you think about pictures like this? Well, it's another one of these scenarios. You got to be prepared for both. And it depends on the physical scenario. If you're talking about light bulbs, you want to think number 2. And if you're talking about, I don't know. It's a weird, I suppose I have a bucket full of birds. Right? And the birds are flying out. Yeah, the birds are flying away. I'm losing birds. So either is plausible. Okay, more to say on that in chapters 6 and 7. Another quick example. By the way, another nice little exercise. Please do make a note and take the time and try to persuade yourself that this is what that vector field looks like. Couple of nice observations I'll make to help you with that. First, be on the lookout for the fall. Oh, I'm sorry, you had a question.
So the previous page,
Yeah.
do you mean like for both cases, is the density decreased?
Nope. No, because with photons it doesn't. Right? So if you take a light bulb, again, there is no store of photons in there. It's producing photons and they all leave. And so your photon density is constant, 0 on the light bulb. So yeah, it's sort of a one or the other. And you want to hear where it gets really annoying is that sometimes it's both in kind of a combination. It's like, well, to some extent one and to some extent two. And that's another thing that we're going to talk about as a scenario. Like how do you distinguish to what extent one and to what extent two, and what does that even mean? And we're going to talk about that in chapter 7. I'm pretty sure it is. Yep. Okay, so make sure you can draw this. Hint number 1, notice the field vector doesn't have any x's in it. Always be on the lookout for little freebies like this. When the function you're interested in is, conspicuously missing one of your independent variables. There's some convenience in there. And in this case, what it means is that it looks exactly the same no matter what x is. So that's why these field vectors here for this value of x look exactly like these field vectors representing this other value of x, because x doesn't matter in the formula. Right? So that's the foot in the door, fill in the rest of the blanks and persuade yourself this is what that looks like. And now let's play the game with divergence. You compute the divergence. You get 0. So that suggests that wherever we're looking, and notice here I'm not confining myself to the origin. Here we could be looking anywhere, and let's say there. What this is saying, when we say divergence is 0, what it's saying is that there's just as much inward flow as there is outward flow. And again, I think that tracks with this picture. Right? There's just as much flow inward as there is outward. It's kind of canceling, if you will. There's sort of a negative outward flow on the left side, positive outward flow on the right side, and apparently they cancel. So, okay, just another sort of, again, it doesn't prove anything, but it just kind of tracks with the claim. Okay, example number 2, apology number 2 incoming. I'm going to write something down. I'm going to make a baseless assertion as to what it means, right? And then, sorry, I'll make up for that later, right? I owe you a justification, and that'll be in chapter 6 and 7. Okay, so this one is called curl, which is denoted like this, and is computed by this wacky formula here. So it's like double symbolic, right? It's a symbolic determinant, kind of triple symbolic. It's a symbolic determinant that involves a matrix full of 3 vectors, the first of which is a symbolic vector, the second of which is a different kind of symbolic vector, right? So, well, again, if you ignore the fact that this doesn't really quite follow technically the rules, if you just take this as a notation, just write it down and compute it the only way that would possibly make any sense, it gives you the formula for this thing called curl. And you can write that down in terms of an explicit formula, and you can memorize that explicit formula, and you will 100% forget that you've just memorized. That's the way the human brain works, unless you're some rare type of person that doesn't, So I have never memorized that formula in my life, not even once, not even for tests. This is the formula that I remember. And I just go through I let the determinant do my bookkeeping for me. Again, it's just like with cross product. again, that's the notation. Just like with cross product, let the determinant formula you already know do your bookkeeping for you. And all you got to remember is standard basis vectors across the top, del vector across the second row, and then whatever vector field you want to take the curl of in the last row. Okay. All right. And again, easier to confirm here, but yeah, it's literally a cross product. Del operator, vector field, and our formula for cross product is like so with the standard basis vectors on the top. So old news. Okay, again, why do we care? Why would we write down this oddball construction? Well, again, because I'm just going to make a claim, but what curl represents is, now in this case, not a flow outward, but sort of a flow, I got to be sloppy about this, but what we call a fluid that's circulating. You think of it as kind of a rotating or a stirred, kind of this twisting, right? I don't know what you'd want to call it, but a rotation of the fluid. Specifically, we're going to use the term circulation, and I will make this more precise later. But think of it as a kind of a rotation. So again, not proving anything, but at least kind of an example of this in action. Here's a vector field. It looks like this. Make sure you can persuade yourself of that. It's a lot like the stirred pot, except this is three-dimensional now, which I guess is really technically more pot-like, right? And if you compute the curl, yada, 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 details, make sure you can do that. The curl ends up being this vector like that. And sure enough, notice the fluid is kind of rotating sort of around that curl vector. And so in general, in fact, what we're going to find is that when you have a curl vector, it tells you two things. It tells you around what direction is there sort of a circulation of sorts, and you can find that later. And the length of the curl, in some sense, tells you whether it's a lot of fluid rotation or some sort of a gentle, slower rotation. Yeah.
No, I was just asking about whether the magnitude and stuff.
Good. Okay, so by its magnitude and its direction, it's describing, in some sense, this circulation of fluid. Yeah.
So, but in this case, for this construction, the sign doesn't matter.
The sign does matter. Yeah, no, it's a great question. I hear you. So the right-hand rule. So if you put your thumb in the direction of the curl, that's your thumb of your right hand, then the fingers of your right hand will sort of, if you will, rotate around your thumb, right, in the direction of the circulation that's happening. It's always kind of a right-hand rule. Yeah. Okay, another easy example. Pretty easy to persuade yourself. That vector field looks like this. Pretty easy to persuade yourself. I don't see any rotation of anything here. And you compute the curl, you get 0, no curl, no rotation. Again, that tracks. Pretty straightforward. Okay. This is the weird one. I think very important example. Looks at a glance like a counterexample. Because check this out. This vector field, again, make sure you can draw that picture. Think it through. Make sure you can draw that picture. Good exercise. The flow lines are all straight lines. It would be very tempting to say, well, they're all straight lines. There's no rotation. What rotation could there be? Everything's moving in a straight line. I claim there is a hidden rotation there. And curl notices it. If you compute the curl and, yada, 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 play the game, right? There it is. It's non-zero. The curl suggests that there is a circulation here, and in fact, there totally is a circulation. So what gives? How come the seeming inconsistency? And this is part of the, what I'm going to call confess some sloppiness in how I've defined the term circulation. Right? The very first example that I showed you of a circulation has the feature that the flow lines are also curving. And there is a tendency for students to grab onto that fact because it leaps off the page at you. And to think that when we say circulation, we mean curved flow lines, and we don't. That's actually not what circulation is. What circulation is, well, and again, it's a definition we're not really quite ready to make, but here's how I think the better way to think about it. Again, imagine that this is a fluid of like water or something, and again, imagine that you toss a bay leaf in. The bay leaf has some dimension to it. It has some size. What would that bay leaf do? Well, it might move one direction or the other depending on where I put it. But you know what else it would do? It would start turning. It would start rotating. Right? Because check it out. It's being pushed. It's being pushed that way on that side, which suggests a rotation in that direction, but it's being pushed by the fluid that way on this other side, which suggests a rotation, you might say, in the other direction, but here's the thing. This rotation and that rotation, they're kind of the opposite, but they're also kind of the same, aren't they? They're both sort of clockwise, which I call clockwise. This is a better intuition for circulation. Don't look at flow lines. It's not about flow lines. Flow lines are not the point. And when we eventually do write down a definition of circulation, flow lines aren't going to be involved, not even a little bit. But when we do write down that definition of circulation, you're going to notice that, it's highly consistent with the idea of how does the bay leaf rotate. And now let's play the game with the curl. The curl downward, thumb of my right hand, got to use the right hand, thumb downward, fingers of your right hand, notice, would have you going around exactly the direction that the leaf rotates. Is that cool? Okay, so the purpose of this example is to dispel a misinterpretation of what circulation is, and therefore what curl is. Yes?
So if you do it like that, wouldn't it be clockwise?
Yep, it is clockwise.
So when in the bottom it's just like...
so counterclockwise as seen from below. And so, again, this whole clockwise counter, when you're in 3 dimensions, it depends on which way you're looking from. So, look at my finger, right? To me, this is clockwise. To you, it's counterclockwise. Right? So I claim that this, let's see here, we would call this clockwise until you go down and look at it from below, and now it looks counterclockwise. Does that make sense? So that's what I mean here by counterclockwise from below. You always kind of got to think about, if you're in 3 dimensions, you got to be careful of the perspective point. Okay, I'm sorry, I'm way over time. So we are done for today. Let's see, let me draw the line. Whoa, I just went way out. So we'll draw the line right here, and we'll pick up here on wait a second, today's Friday. Monday, I guess it's Monday. I don't think Monday is a holiday or anything. So see y'all Monday. Have a great weekend. See you later.